Difference between linear regression and logistic regression. So before we discuss the difference between linear regression and logistic regression, let us first review the linear regression. We have some data, our weight and size. Then we fit a line to it, and with that line, we can do a lot of things. We can calculate the R-square and determine if weight and size are correlated. Large values imply a large effect. Second, we can calculate a p-value to determine if the R-square value is statistically significant. Third, we can use the line to predict size given weight. In multiple regression, we are trying to predict size using weight and blood volume. With that, we can calculate the R-square, the p-value, and predict size given weight and blood volume. Comparing the simple model to the complicated one tells us if we need to measure weight and blood volume to accurately predict size or if we get away with just weight. Now, let us discuss the logistic regression. So, logistic regression is similarly to linear regression, except logistic regression predicts whether something is true or false, instead of predicting something continuous like size. The mice are obese, these mice are obese, and these mice are not. Also, instead of fitting a line to the data, logistic regression fits an S-shaped logistic function. The curve goes from 0 to 1. That means that the curve tells you the probability that the mouse is obese based on its weight. If you weigh a very heavy mouse, there is a high probability that the mouse is obese. If you weigh an intermediate mouse, then there is only a 50% chance that the mouse is obese. Lastly, there's only a small probability that a light mouse is obese. Although logistic regression tells the probability that a mouse is obese or not, it's usually used for classification. For example, if the probability a mouse is obese is greater than 50%, then we will classify it as obese. Otherwise, we will classify it as not obese. Just like with linear regression, we can make simple models. Obesity is predicted by weight, plus genotype, plus age, plus astrological sign. In other words, just like linear regression, logistic regression can work with continuous data and discrete data. We can also test to see if each variable is useful for predicting obesity. However, unlike normal regression, we can easily compare the complicated model to the simple model. Instead, we just test to see if a variable effects on the prediction is significantly different from 0. If not, it means the variable is not helping the prediction. We use Wald's test to figure it out. In this example, the astrological sign is not helping. That means we can save time and space in our study by leaving it out. One big difference between linear regression and logistic regression is how the line is fit to the data. With linear regression, we fit the line using least squares. In other words, we find the line that minimizes the sum of the squares of these residuals. We also use the residuals to calculate R-square and to compare simple models to complicated models. Logistic regression does not have the same concept of a residuals, so it can choose least square and it can calculate R-square. Instead, it chooses something called maximum likelihood. You pick a probability scale by weight of observing an obese mouse, just like this curve. And you use and you use that to calculate the likelihood of observing a non-obese mouse that weighs this much. And then, you calculate that likelihood of observing this mouse, and you do that for all the mice. Lastly, you multiply all of those likelihoods together. That's the likelihood of the data given this line. Then you shift the line and calculate new likelihood of the data. And then shift again, and then again. In summary, logistic regression can be used to classify samples. It can use different types of data to do that classification. And it can also be used to assess what variables are useful for classifying samples.